My name is John Austin, and I'm an independent game developer, and so I'm here to talk about color. So let's set the scene a little bit just to get started. The year is 1931, and that means a couple of things are true. Math is done on slide rules, so there's barely the concept of electrical computing. Electricity is still coming to rural parts of America. Like, there's this big push to electrify the rural America. Like 30% of homes are still without power. And on top of that, at this time, the stock market had just crashed. And this was the biggest depression in US history, but also worldwide, right? Like 16% of the entire world was without work, 25% in the US. And so, in the midst of all of this, a bunch of people decided that this would be a good time to get together and come up with like a unified standard of color. And so a bunch of people met in this dusty room in France and sort of decided to come up with the systems that actually underlie all of the systems that we use today for RGB and the color that we use, even into like kind of the digital era. And it's sort of a testament to sort of the prescience of the work they did there that it still lasts all the way to nearly 100 years later. And in today's world, color is just everywhere, right? It's in our images, it's in like the web, it's in our books, it's in our clothing, right? When you want to go make a new piece of clothing, you need to know what color to dye it, right? Somebody has to tell you what color to make. And in this crazy world of color, we must have these fantastically complex systems to manage the powerful nature of it. But most of us probably just eyeball the sliders until it looks about right. But what actually is RGB, right? Like, what is 100 red? Like, most people don't really have a good concept of it. And so, what I want to talk about today is kind of the history of color. How is it made, and how are these systems made? And then also the science of it, like what are the things we're actually using today, and how can we work backwards and follow the lineage back to the systems that were created in the 1930s. Color is this like crazy, weird subject because it's inherently subjective, right? It's like, what is art and what is beauty and like color perception, right? But it's also, insanely objective. It's, wavelengths, it's light, you can measure it. And sort of in the midst of all of this, there's color systems that try to represent it. And so ever since I learned about this stuff, I've been excited to give a talk on it because it's just, every time you peel back a layer, you get something more and you learn something new about how we perceive the world. So it's just super cool. And so that's what this talk's going to be about. So to start with, let's look at a little bit of biology. So you can think of light as a pipeline. So light bounces around the world, it hits your eye, bounces around inside there, hits a few sensors, and then goes to your brain. And so we can look at each of these kind of components individually. So light is a spectrum. What we can see visibly is a fairly small part of the spectrum, right? So that on the left there is the spectrum of the sun. And most of the light that's put out by the sun is not visible to us at all, right? It's either in the ultraviolet or in the infrared zones. And so this like little chunk of visible light is sort of just biological happenstance. Like there's nothing particularly objective about the visible spectrum. It's just the way we're set up to see. And in fact, heat, for instance, like everything that is hot gives off light in the form of radiation, right? And so that's why you can hold up a camera and see an infrared picture of a heat signature, because it's light in some respect, right? So if we were built a little bit differently, like say we were a bee or like some other animal, we would see just different parts of the spectrum. And so light isn't necessarily quite as light and color aren't as objective as it might seem at first. And so we have this spectrum, right? And it goes into our eye and it hits these things called cones. And the cones are our sensors in our eyes that are primarily responsible for our color perception. So we have three types of cones. We have our short cones, the medium cones, and the long cones. And each of these cones responds to a different part of the spectrum. And you can sort of already see something interesting here, which is that these cones kind of align to red, green, and blue to some degree. It's not perfect. But you can think about why we might use these colors as our basis for color definition, because they nicely space along the spectrum, right? It gives us a lot of resolution in that way. And it's kind of weird too. It's like, well, okay, our green cone is really heavily overlapping on the red cone, right? And we can think about how that might like add some weirdness to the way that we perceive colors around those zones, right? So we have these three cones, and basically each cone ends up kind of producing a number. So if you're looking at this, so let's say you're looking at an apple, and you're looking at maybe just that little pixel, right? Like the 2 degree, part of your vision that is seeing that color. Each of your cones is going to respond in a different way, and so you kind of get these three numbers that are sent to the brain. And you can sort of measure these, you can actually put units on them, but they're more like brain units. They're not, especially in the 1930s, they weren't about to measure these, but now we can with modern technology. But the interesting part about this setup is that we can actually describe all color that we can see with just three numbers, which it shouldn't be inherently intuitive to you, right? Like light is this crazy spectrum of all these numbers and different types of waves, but you only need three numbers to describe every single visible color that you can see. And this is why all of our color systems use three numbers, because that's all you really need at the base level. So, this then also brings up an interesting question, which is like, well, what if you have two spectrums, and maybe they're wildly different, but they map to the same color, right? Because this is a lossy operation. There's way more spectrums than there are, three-digit numbers. And so this is what's called a metamer. And so these are all around us all the time. So you might think that the green of the grass and the green of a lime, the green of tea is all the same color, but in reality these are wildly different spectrums. It just happens to be that you perceive them as the same color. And in fact, this is how modern display technology works, right? It's all about how do you tickle those cones just well enough to pretend that you're seeing the right color, right? They're not actually trying to recreate the spectrum on the monitor. They're just trying to make you think that you're seeing the colors. So we can think about other animals that might be set up differently. So like the humble pigeon, he is a pentachromat, so he has 5 cones. And when the pigeon looks at colors in the world, you might see totally different colors, right? Again, it's this like sort of biological happenstance, right? So like color is pretty weird, right? It seems objective at the start, but the way we describe color might end up needing to be a little bit more brain-like than we might think. And being able to talk about colors is, it's important, right? Like even in the 1930s, this was important. And like, we need some way to say, even though it's all this kind of in your head, right? We need some way to be like, oh, hey, this is the color I'm talking about. And, back then, the main concern they had, they didn't have monitors, right? But, they had signal lights on planes and boats. And so like, as the world became more globalized, it became important to, know what colors are on different ships, right? Like if you tell your ally that, you have green on the left and red on the right, like you best be sure that you know what green and red you're talking about so that you can, communicate properly. So, this seems kind of trivial, but this actually drove a lot of the color science research that defines all the systems we use today. And so, enter the CIE 1931 International Commission on Lighting. And so this was basically a big convention with a bunch of different countries. And sort of the plan was, okay, we're all going to get together and we're going to vote on a specification that defines a standard for color. And then, they had sent out this specification ahead of time because, back in that time, communication was hard and tiring, and so they needed some time to kind of look over stuff. And sort of the two big heavyweights in this convention were Britain and the US, and they had been doing most of the color science for the past decade or so. And one of the big players from England was a man named John Gill, and he worked at the National Physical Laboratory there. And John Gill was pretty excited because it was his system that was to be voted on at this conference. He had come up with this system of additive primaries, which is just to say that you can add colors together and you get new colors. And it's kind of abstract, it didn't really represent a closed system to the way that humans think about color, but it had all these mathematical properties that were really nice. And yeah, so this is the system they were going to be voting on. And so there was another man at the conference, and his name was Irwin Priest. So Irwin Priest was the representative from the United States. He was the president of the Optical Society for America. And when Irwin Priest got off the boat, he was mad. He was livid. And It might have been for good reason. I mean, I mentioned that they sent out those resolutions ahead of time, but they had really only sent them out about a month in advance, and like that wasn't nearly enough time to actually study them or do the rigorous kind of scientific research to actually judge them so they could vote on them. So he was a little miffed by that. But the other thing was that the US actually already had a system of color. So they already had a standardized system. And they had adopted this system a few years earlier. And the US system was not based on this additive primary stuff. It was based on something a little more pragmatic because it was driven by industry. So it's basically based on these things, hue, saturation, and brightness with different names. And we might recognize that from today, and we can think of like, well, why do we use that in our color pickers? Because it's it's inherently kind of just a very pragmatic way about reasoning about color. So he was angry. He was ready to fight. So what did he do? Well, he arranged for himself to arrive a week early so that he and John Guild could have a talk before the conference. And over the course of an exhaustive week, they kind of went back and forth debating their different systems. And one of the cool things about John Guild's system is, even though it wasn't very pragmatic, it had this property that it could be transformed to other systems. So because it had these mathematics, he basically showed how it should represent priest systems. So he slowly transformed it to priest system to show how it's a better standard, even if it's not as pragmatic. And then so basically over the course of the week, they settled on a final set of systems. And so they scrapped the original systems that they sent out, much to the other countries' chagrin. And so they presented a new set of resolutions called the CIE 1931 Resolutions on Color. And so these are the systems that we use in a lot of ways that define like all of our color spaces that we use. Or at least the fundamental bits of it. So the question remains, well, okay, what are these color resolutions, right? And like, what is RGB, and like, what is a color space? Like, what are all these things? So that's kind of what we'll spend the rest of the talk doing. So like, we'll go a little bit through the science of it and kind of explain what are these systems, and we'll work our way all the way back to where we are today in the present. It's not too much, don't worry. All right, so let's go back to John Guild's system. So at the end of the day, it was basically his system that was accepted with some modifications. And his system was based on this concept of additive primaries. So back in the day, you couldn't measure color. So if you wanted to actually measure the spectrum, you'd need a spectrophotometer, and that hadn't been invented yet. So they had to be a little more creative. And so he came up with this experiment where you put a target color on the left, say this kind of green color, and well, anyway, yeah, so let's say you have this target green color, and you place 3 colors on the right that you do know the wavelengths for. Maybe you can prove this through physics or through some other means. And then you sort of add and subtract them until you make up the color on the left. And so that kind of gives you 3 numbers, right? It gives you how much of each of those primaries did you need to make up that color. And so, he did this with a bunch of different colors, and if you plot those in a 3-dimensional space, with each axis being kind of, the amount of that color, then you get this volume of color. And this, inherently, this is a color space. It's a space with a bunch of colors in it, and that's basically the most general definition. Color volume is another word for it, right? And the interesting thing about a color space is that you can do math in this color space, which also should not be very intuitive at all, because color is this crazy spectrum. But as it turns out, you can take the 3 numbers from this color space that John Guild was working on, and you can add them together. And the color you got as a result would be the same color you'd get as you would in real life if you had overlaid those lights. And so this property, which is like kind of amazing, is like the fundamental basis of how we use color. It's the reason we can do math on color at all, which isn't necessarily a given. And so they were realizing this at the time, and so that's how they put together these early color spaces. So he sort of set about making this first color space, right, and mapping out the visible colors. But he came up with this problem, and it's easiest to describe this problem if we go back into 2D. We do this a lot in color science because reasoning about volumes and showing them is really hard. You can't look inside them easily. You need to render them. It's a total pain. So a lot of the time we project it down into a 2D space. So if this is all of the visible colors that we can see, right? And we're John Guild and we've picked 3 primaries. Maybe we put them here, right on the edges of visible color. Then all the colors we can make are inside of this triangle, because those are the colors that can be blended between those 3 primaries. And so the realization here is that you can't actually recreate all visible colors with a fixed set of primaries. And that should make you think, well, that also means that today, right, if you have a monitor, you can't actually make a monitor that can represent all visible colors. It's impossible if you just use a fixed set of primaries. In fact, if you have $6,500 to burn in your pocket, you can go buy a laser TV that has like no less than 6 laser primaries, and it gets you pretty dang close, but it's still you're only inching your way to covering this volume. So he realized this at the time, and so in order to map out the space, he needed to be a little more creative. Let's say you have this cyan color, and so some of these colors are gonna, the color space of this display is limited, the projector is. So you'll have to imagine some of this, but I think it should work for the most part. So let's imagine you have this cyan color that you can't make with these other 2 primaries. What you can do instead is you can add a color on the other side and sort of treat it like a negative color. And if you do that, then you actually can make those colors equal. And so by using this sort of negative trick, he was able to map out the full color space. And what he created was something called CIE RGB. And this is the first color space. It's sort of the granddaddy of all historical color spaces. And it's different than the RGB you're thinking of. This is CIE RGB. And it just happens to also use red, green, and blue as the primaries. And you can sort of see, there's the negative colors hanging off the back there. But, what was really cool about this is now we have a way that we can talk about colors. The Navy can come to you and be like, we need some color for our colored glass. And they'll be like, oh, well, that's a negative to 0.7, 0.6. And you know what you're talking about. You can go look it up. And what you can do is you can take that number and transform it back to the spectrum. You can sort of use a scientific process to kind of test your glass until you know that it's properly recreating the color you want. And so this is a big invention, right? Like now we can finally reason about color in a very objective way. But this color space, it's got a lot of problems, right? Its negatives are super weird, right? Like what is a negative red anyway? And like you're doing math on slide rules, like negatives are awful. And this is one of the big criticisms of priests too. And what are the boundaries of this, right? Like it's sort of based on this experimental methodology. It's not that great. And so what they realized is they needed to make a more ergonomic color space. And we talked about how color spaces can be transformed. Like that's the big property of color spaces. And so what we can do is, well, let's transform this color space into something more mathematically ergonomic. Let's just stretch it and squish it into something better. So, and then here's a big point about these transformations, is that they have to be linear. And basically all linear means is that the origin has to stay in the same spot, and lines have to stay straight. An easy way to check to see if your transformation is linear is, can it fit in a 3x3 matrix? If you can, it's linear, you're all good. Otherwise, you can't. And so it's important that you need this linearity property in order to get that mathematical behavior we talked about, right? As long as your transformation is linear, then addition and subtraction in that new color space will still recreate the properties of real life. And so this is the property we want. So, they set about making this new ergonomic mathematical color space. And, again, they were kind of clever. They realized that, well, okay, previously our primaries were in the visible color space, but if we choose our primaries to be imaginary, then we can stretch our color space to be entirely positive. And this is super weird. It's like only mathematical, right? Like you can't represent these colors at all in real life. And so they called it XYZ because, well, these axes don't have any meaning anymore. So they were like, oh, we'll just call them XYZ. And XYZ is great. Like it's mathematically beautiful. Everything's positive. It's all less than 1. They put white at 1/3. One thing they did as well, here's like a 3D sort of representation. They aligned the y-axis with brightness. So if you want to know how bright a color is, you just have to look at the second value. Super easy. And so, CIE XYZ, this is, nobody really talks about, all these other color spaces before CIE XYZ. Like XYZ is kind of like the main player in today's world. If you want to make a new color space, let's say you're Adobe, you would provide a transformation back to CIE XYZ. You can go on Wikipedia and you can find the 3x3 matrices that get you back to CIE XYZ for all your favorite color spaces. And in doing so, that sort of proves that it's a valid color space, that it represents all visible colors and that you can transform between them, right? So, flashing forward to 2019, now we're in the digital world, right? So that's sort of the end of the 30s, with CIE XYZ. But now, colors everywhere. Like we have all these other concerns about monitors and displays and images and computing and so in the 70s, they realized that they needed, a color space that was really built for the digital world. And this color space is called sRGB. And this is the color space that you've been waiting for. This is like the standard RGB. And so when you use that color picker in Chrome or Photoshop, it's in sRGB. That's the color space of the values you're specifying. And it's easiest to show sRGB. It's a color space like all the others, but we usually show them against XYZ. Because XYZ is this sort of like forefather of color spaces. We can kind of compare them. So if we show the 2D visible gamut of CIE XYZ, we can say that okay, sRGB is a subset of it. And we know it has to be a subset because our monitors use visible primaries, right? You have to, the corners of that triangle have to be visible colors, so it has to be a subset. But it's a particularly small subset too, which you might wonder why that is. I mean, it was originally designed for CRT monitors, and CRT displays couldn't show anything more than that. So why would you waste the bits? We can also show that in 3D as well against kind of CIE XYZ, and you can see that it's not it's not a triangle, right? It's really this 3-dimensional prism shape, but it's a lot thinner, right? It's missing a lot of these more interesting colors. An interesting to note about this, right, is you're looking at this right now in sRGB, right? This display uses sRGB. So this entire presentation has been compressed, right, down into, it's been projected. And there's all sorts of transformations you can use to project it. But what you're seeing right now is it's like a relative, judgment of these color spaces. So those greens, that seem to be missing, you can't see them anyway, so. Anyway. So sRGB, like the others, is just one more transformation. So you get this kind of mathematical lineage coming. sRGB, it's kind of this universal transfer format, right? Everything uses it. But it's got this weird quirk, and it's easiest to explain it if we talk about kind of human perception. So when you look at, let's say like a linearly increasing brightness of color. We're much better at telling the difference between darker colors than brighter colors. The big bright whites kind of wash out to us, whereas we can find a lot of subtleties in the darker colors, relatively speaking. And so they realized this in the 70s, and they decided, well, in that case, why don't we not spread our bits uniformly? We'll put more bits down at the part we can tell the difference between. Which makes a lot of sense, right? If you're really bit limited, it's important that you spend those really on the parts that are most important. And so what they did is with this 3x3 matrix, they also applied this extra operation, which is called the gamma curve. And it's essentially a square root. It's a piecewise. It's not exactly a square root, but generally you can call it a square root. You can look it up on Wikipedia, but. Essentially, what this curve does is, spread out the color space such that it's kind of a little more optimal for storage. But the weird thing about this extra transformation is that it's not linear. And we made this big fuss about, how we want our transformations to be linear so that so the math works in the new color spaces. And so that what actually ends up happening is that math in sRGB is not correct. And so what that means is that if you add 2 colors in sRGB, like the color space you use every day, you won't get the color you would get if you added them in real life. And so this is sort of like the perpetual problem of like incredible amounts of software. If you take away like one thing from this talk, it's that you probably shouldn't be doing math in sRGB. Like convert it to some other color space, any other color space, basically. But sRGB is still important because it's a universal transfer format, and it's got great bit density and stuff like that. But like you might think that maybe this isn't a big deal that much. But so let's look at an example. So back in 2010, most game rendering at that time was being done in sRGB directly because that was the color space they were using. They didn't really have the performance to think about it too much. And what you get is you get all of your light being thrown through this exponential function, and so like your whites get crunched and your darks get crunched, and it looks really awful. And so after 2010, they started doing physically based rendering, and everything looked much better because what they did was they used a linear color space. And generally what most game engines use nowadays is something called linear sRGB, which is essentially to say it's sRGB, but they don't do that extra gamma curve. They don't do the square root. They just drop that. So then they keep the whole transformation linear, and that makes it a linear color space, so everything's good. And then you get these much better colors. Okay, so we've got our 2 main color spaces now. We've got like sRGB, that's what you use. But if you want to do math on it, you should probably be using something linear. But it's not quite the end of the picture. There's lots of times where maybe we don't want scientific accuracy, right? Like this has all been about recreating the properties of real light. We've been trying to find color spaces that let you, recreate these behaviors of like overlaying lights in the real world. But sometimes you want to do something like more artistic. You care more about perception. So like let's look at an example. So this is a constant brightness slice of the sRGB spectrum. And what that means is that the intensity of the wavelengths of light that are leaving the screen and going to your eye are all equal, or at least the projector is doing its darndest to try to make it equal. And what you can notice about this is that these colors don't look perceptually equal in their brightness. We have this tendency to perceive yellows especially as particularly bright compared to corresponding blues, and same with whites. And so our color perception is not perceptually smooth. And so let's look at another color space. So there's this color space called CIE Lab, and CIE Lab is a color space that's built to spread it out such that the color space is fully perceptually uniform. And so what you get is this incredible, like, smooth gradient of what looks actually perceptually uniform. And the weird thing about CIE Lab is that CIE Lab intentionally does these nonlinear operations. Right? It's no longer accurate to real life, but it does them intentionally such that when you do math in CIE Lab, it makes something that looks more perceptually correct, which I think is really cool. Like, CIE Lab totally blows my mind. Like, there are a few things that you can do where you can just drop something into your project and all of a sudden it looks 10 times better. CIE Lab is basically the secret gem of the data visualization community, like D3JS, all these people, because all of these visualizations are driven by data and math, right? And so they want these crazy nice linear gradients, right? But if you do a gradient in RGB, you get this kind of dark spot in the middle. It's a little easier to see if you squint sometimes. And the projector's a little rough. But basically, if you try to interpolate the RGB, the color space wasn't built for interpolating. It was built for math, like adding and subtracting. And so sometimes you can get these weird hues that just pop out of nowhere. But Lab was built for uniformness. And so it's when you interpolate through Lab, you get these great gradients. So this is like really what powers data viz. And let's look at one more example of Lab just because I think it's so cool. So, you might think this is a pretty trivial operation. Like let's say we want to desaturate an image, right? Just make it grayscale. And so we take this painting of a sunflower, right? And it might look pretty similar, but look at that sunflower, right? So we've grayscaled it in RGB at the top, in linear RGB, so this would be correct to real light, right? But that sunflower is super dark compared to lab, and we can sort of zoom in just to emphasize that point. Like look how much worse it looks. And one thing you can kind of note is like on the edges of those petals there's these like little white spots. And those white spots aren't really present on the original image. It just so happens that these like two hues you work out such that the actual intensity of light is like really different. But to our brains, we see them as very perceptually similar. And so when you're doing grayscale, like it might seem like a super simple operation, but it's actually a perceptual operation, right? We want to know what looks like the brightness of each pixel. And so we should do that generally in lab. And so I would suggest that if you're doing some math on color, that you think a little bit about which color space you might want to use. I prepared a little bit of a table just to kind of help with that. And these slides will be up online later probably too. But if you care about science and rendering, and you really want to create correct to life light, right? Then you want to use linear color. You can use linear sRGB. There's lots of other linear color spaces. But if you care about perceptual correctness, right, and you want something that's smooth and uniform, CIE Lab is definitely something interesting to reach for. I definitely recommend trying it out. And of course, we have to use sRGB because everything expects sRGB. Our monitors expect it. The web expects it. So at the end of the day, we still have to use it. But we should probably get it out of sRGB as soon as possible. I mean, like for instance, like new MacBooks, right? They have better monitors. Like part of the reason they look nicer is because they render a bigger subset of the visible spectrum. But of course, that means if you're sending sRGB to your MacBook, you're not taking advantage of that nice spectrum that it can render. So you should think about, even if you are just rendering something to a display device, like what display device is that? And maybe you should use a different color space so that you can take advantage of those properties. So that's about it. Thanks for listening. You can follow me on Twitter. I post about all sorts of crazy games and art and math and whatnot. Quick thanks to the CIE, which is apparently still around and kicking, and helped me come up with some primary sources and track down some articles from the original conferences. But yeah, I have absolutely no clue if I have extra time. 5 minutes? I can take some questions, yeah, if you have them. And then otherwise, I'll just be outside. Yeah?
Is CIE Lab still a subset of the color space?
Right, so CIE Lab is, so you can see up there on the top right, that's the visible gamut of all colors in CIE Lab. So it does represent all visible colors. So one of the downsides of CIE Lab is that it's not a subset, but that means you need floating point numbers. So CIE Lab is not an additive primary system. It's based on 3 numbers. It's based on lightness and then A and B. And where A and B are basically like the color, but because it's not based on additive primaries, they don't have that restriction where it has to be like just a subset of the visible spectrum. And so it's a lot more like XYZ in that sense. It's also a little weird because lab by default it's not in the range 0 to 1, it's 0 to 100 for some unreasonable reason. But yeah, it can represent all visible colors. Yeah. Yeah.
When you render these images, right, the spaces, are we looking at just the surface of them? Or are we looking at something that reflects what's happening inside? Is something of that happening inside even meaningful?
Right. Yeah. So the question is, when you're looking at these 3D volumes, like what does that really mean? What is the reasoning behind that? So yeah, you're looking at this essentially the surface, and the reason we do so much in 2D is because with these 2D slices, is because yeah, you can't see into this volume, right? Yeah, like really, it's basically like you could take a slice throughout the entire thing like a cross section, and you'd see different colors changing, and so like it's a volume, not a surface. So there's colors inside of it. Yeah, hopefully maybe that answers your question.
Speak or give us any tips
That's a good question. Yeah, man. I would have loved to talk about print because there's so much there. Like, there's all sorts of crazy different color spaces. I had to leave a lot off for time concerns. So print is based on something called CMYK. And so that's 4 numbers, which is odd. But print is unique because it's a lot more driven by the sort of material science and like the actual process of making and printing things out than it is by trying to represent colors mathematically. So CMYK is, cyan, magenta, yellow, and black. Technically, it stands for key, which is like an old term, but yeah, anyway. So CMYK is also weird because it's device dependent. So like all these color spaces we've been talking about, a single color represents a single color. Like that's what it is, that's the color. But CMYK, it depends on what printer you're talking about, what kind of ink you're talking about. So like you might have CMYK this number, but it only represents a certain color if you know what ink you're talking about. And if you change the paper, everything changes because the reflectance changes. CMYK is also subtractive, which is a little weird in the sense that it's CMYK because cyan represents the removal of red, right? So if you add cyan, that's like removing red, and so there's a lot of messiness in there. It's also dotted, like it's actually what's called halftoning, which is kind of like what comic books use, where they kind of dot everything to sort of blend the colors in your head. I would definitely I take more questions afterwards if we could talk a lot about print, but yeah, it's very interesting. Sure.
Given that monitors are displaying RGB, why do 2 monitors display different colors, but the same color in different ways?
It's because they're bad monitors. Yeah. This is why people who work doing art for a living care a lot about getting a really nice monitor because okay, so it's the last question, I guess. So yeah, like not all monitors are made equal. So like we talked about, like you have this RGB color space, and you want to go back and map that back to the spectrum, right? But that's a really hard transformation. It's like, okay, how do I get these LED lights to like get the right colors and tickle your cones in the right ways? And so cheaper monitors just do a worse job at it. And you can actually buy something called a spider, which will sit on top of the monitor, analyze it, and then recalibrate your monitor to the best it can, which I don't know if I'd recommend for everyone, but if you really care about color, that might be something to do. Okay, well, I'll definitely take more questions outside, but thanks for coming. I hope you learned something.